Well, thanks very much for the invitation to speak at this very interesting meeting. I should apologize right from the beginning that I'm not going to say anything about pharmacogenetics, but I hopefully say something about that's relevant to the question of stratified prevention and medicine. So we saw an earlier version of this slide from David Hunter this morning, the catalogue that's continually being updated of all the genome-wide association studies that have been identified for many, many traits. And there are literally hundreds of thousands of associations which have been identified. It's pretty amazing considering there weren't any before about 2006. So the progress has been quite extraordinary through the advent of these large genome-wide association studies. So I'm particularly going to talk about cancer, and mostly about breast cancer, which is the disease I've mainly worked on. For breast cancer, most of the data has come through the large consortium, the Breast Cancer Association Consortium, which has conducted GWAS of something like 150,000 cases and controls, and identified something over 200 independent loci, illustrated on one of the Manhattan plots here. You'll see some gene names here. Of course, most of these, and this was touched on also this morning, in most cases, the variants which are associated are not in genes. In most cases, the signal appears to be regulating a nearby gene, and in some cases, we have some idea what that gene is. But in most cases, we don't really have a very good idea of what the underlying biology is. And in many cases, we don't even know what the target gene is. Some of them could be promising drug targets, but that's really work for the future. Certainly some promising examples. Polygenic risk scores, in a sense, ignore all that. They're treating these variants sort of agnostically. And the point here, illustrated a bit this morning as well, is that the individual effects of these variants are very small, but there are an awful lot of them. And so the combined effect of many risk alleles is substantial in the population. So if you just take everyone in the room and you simply count up how many risk alleles they have for a given disease, like breast cancer, you get a distribution, a normal distribution. So nobody has all the risk alleles, nobody has none of them, everybody is somewhere on this distribution. And because they are associated with risk to some extent, cases of the disease have more than controls, and so you get this shift between the two normal distributions in cases and controls. And the amount of that shift really is really a summary of how useful these common variants are at predicting risk. Now, somebody was asking me earlier, why do you just add everything up? And that's a good question. I mean, you might think that there are lots of complicated ways of constructing risk scores based on these hundreds or thousands of risk loci. But it turns out that you don't really gain very much beyond a simple weighted sum. So there don't seem to be much in the way of interactions between different loci. This sort of weighted sum is the best thing to do. So a polygenic risk score is just a sum of the number of risk alleles weighted by effect sizes. And so again, you get this shift in the distribution in the population versus the controls, if you like, versus the cases. And there's various ways of measuring it. So a simple way is just to look at the difference in the between the cases and the controls. And this measure here turns out to be the same as the log of the odds ratio per one standard deviation of the polygenic risk score. And from that, you can predict lots of things like what would be the area under the curve, or what would be the proportion of the population that would at any given risk, or what proportion of cases would be identified at any given risk. Now, that still leaves open the question of how many SNPs you should put in and how you should define those weights. And there are certainly lots of ways of doing that. But I'm going to talk for concrete reasons, about one specific PRS, which we developed using the data from the BCAC, which, after a lot of pre-processing and several stages, comes out to have 313 SNPs. So basically, you're ranking all the SNPs and then identifying the most significant and thinning them out and replicating until you get down to this number. It's roughly all the SNPs that are significant at about the 10 to the minus 5 level. And then we go through the stage of validation. That's extremely important in prospective studies, either case control study, prospective nested case control studies, or cohort studies. We did about 12 in the end. And that's shown on the right here. And you can see here, UK Biobank down the bottom, another plug for the UK Biobank, plus all these other prospective cohort studies. And what you can see here, this is the effect size, this is the relative risk per one standard deviation. They're all essentially the same. It's remarkably consistent. About 1.6, you couldn't get any, there's no evidence of heterogeneity between in the effect sizes at all. So we don't have many things in medicine that are as reliable as that. Of course, what we really want to think about this is in terms of absolute risk rather than relative risk. So this is summarized in a different way. So this is looking at the lifetime risk of the disease according to where you are on the polygenic risk score distribution from the bottom 1% to the top 1%, based on the rates in the UK. And you can see there's this huge variation. So the women in the bottom 1% have a lifetime risk of about 3%. In the top 1%, it's more than 30%. So more than 30%, that's high. That would be counted as high risk, according to the NICE guidelines. That'd be eligible for things like MRI screening. On the right here, it's looking at it a different way. So this is looking at the 10-year absolute risk of breast cancer. Again, depending on where you are on the PRS distribution. This red line here, that's a risk of 2.7%. So that's the average risk in the breast screening population of women between 50 and 64. So in the standard screening program, everybody all women between the ages of 50 and 64 gets offered mammography in this country and most other countries. What you can see here, though, is if you did it in terms of the PRS, people would reach this level at very different ages. So at the top of the top 1%, you'd reach this level of risk by about age 30. And at later ages, your risk is way more than that. So you can see why some sort of enhanced screening or earlier screening would be relevant for those women. At the bottom end, these women don't reach this level at all. So you could argue that these women should have less screening, or perhaps no screening at all. You can also look at the effect on the type of cancer, and this is something which might be relevant in the realm of chemoprevention. So there are many subtypes of breast cancer, but the most important distinction is between ER-positive and ER-negative disease. So the ER-positive disease are the ones that respond to hormonal treatments like tamoxifen. And we see that, in fact, the PRS is a bit more predictive for ER-positive disease, which is the commoner type and where there's more data. And more of the loci are associated with ER-positive disease. It is also predictive for ER-negative disease as well. So this is relevant because ER-positive disease is the disease which would be preventable by, for example, tamoxifen or aromatase inhibitors. So it might be relevant in the context of chemoprevention studies. Another possible clinical relevance is that the PRS not only predicts the risk of the first cancer, but it also predicts the risk of the second cancer. So women who have breast cancer, have a substantial risk of a second contralateral disease. And again, this can be relevant in the context of deciding relevant treatments in terms of preventing the second cancer. What we know much less about is the prediction of prognosis. We do know that the PRS is a bit predictive of better prognosis disease. We already saw that it's a bit more predictive of ER positive than ER negative disease. It's a bit more predictive of low grade versus high grade disease. So it's somewhat predictive of better prognosis. But the effect is quite weak, and we don't really have good predictors using common variants, at least, of recurrence or outcome survival, for reasons which we still don't understand yet. But perhaps one take-home message is we really need better information linking the germline genetics to the tumor genomics. So if one had one wish for the UK Biobank, it would be to have better information on the tumors. Anyway, that's a little bit by the by. Of course, PRS have been constructed for many cancers. Here are the four common cancers for which screening particularly might be relevant. So prostate, here, breast cancer, colorectal cancer, lung cancer. And they all have PRS that are predictive of risk, but to a different extent. So prostate cancer, this is very much work led by Ros Eels, in the audience, is the best in some sense. It has the biggest effect size, the most SNPs with big effect. And at the opposite extreme, lung cancer, many fewer SNPs, much less predictive. Breast and colorectal cancer, somewhere in between. And the reasons for these differences are because we don't really understand. That's reflected again in the differences that you see in the absolute risks. So these are data from UK Biobank, applying the sort of most recent PRS to UK Biobank data again. And you can see, really extremely good stratification in prostate cancer. Still good for lung cancer, but not as good, and colorectal and breast cancer somewhere in between. So how might that information be used? Well, most of the interest has been in using this information in the context of screening, so risk-adapted screening. So here are some of the diseases that one might apply this to. So breast and colorectal cancer, we have national screening programs. Prostate cancer, we don't, but might have. Lung cancer, also with CT scans, also being investigated. Ovarian cancer is another possibility. And there are various ways this information could be used to adapt the screening. Well, one is whether to screen at all. You could change the age at which the screening starts or stops, or the frequency of the screening, so moving from, say, 3-yearly screening to 1-yearly screening, or changing the modality. So in the case of breast cancer, changing from mammography to MRI screening. There's also interest in other forms of prevention, so we discussed a little bit risk-reducing medication, or for higher-risk women, surgery, so mastectomy in the case of breast cancer, oophorectomy in the case of ovarian cancer. And there's also potential applications to newer screening technologies. So David didn't talk about this so much this morning in the context of Our Future Health. One of the interests is trying to evaluate newer screening technologies using, for example, ctDNA. If any of that works, then it's likely that that's going to be most useful in the individuals who have the highest risk. And one of the best ways of predicting that would be to use polygenic risk scores. Now, it's fairly easy it's in a sense rather obvious, but it's fairly easy to show that risk-adaptive screening would be cost-effective. So this is just some work from Nora Bashayan, looking at the effect of risk-adapted screening for breast cancer. and looking at what happens if you screen an increasing proportion of the population. And what you see, as you'd expect, is that as you increase the proportion that are screened, the cost of the screening program goes up substantially. But beyond a certain point, you don't really gain anything in terms of quality-adjusted life years. So that points to the idea that it would be more effective in a purely cost sense to screen just a proportion of the population rather than all of them. But the real question then is, will any of this really work in practice? And there are a whole number of studies, both for breast cancer and for other cancers, trying to evaluate that. This is just an example of one of them, the MyPEB study, which is a European study. All the studies have a rather similar design. So you have a standard screening arm based on current guidelines. And then in the risk evaluation, you have this stratification into low, moderate, high, or very high risk. So the idea is that the low risk group gets less screening, the moderate risk group gets whatever the screening is now, the high risk group moves to annual mammography, and the very high risk group moves to what we would currently offer to very high individuals, risk individuals, so mammography and MRI. So these studies are ongoing, so we don't have any results yet. Particularly, this is very much work in progress. But it'll be interesting to see how it really pans out, both in terms of the effectiveness, but also the acceptability of stratified screening in the population. So, of course, one of the challenges with polygenic risk scores is it's a moving target. So what's best now won't be best next year or in a few years' time. And that's sort of different from the situation with single gene variants, where at least you kind of know where you are. So that's a rather a challenge. So this just illustrates what might happen for a whole series of different cancers. These are some predictions done by Nilanjan Chatterjee's group. And what you see here, so it's different for different cancers, but the blue dot is kind of where we are now. And then the red dot is what would happen if you doubled the size of the GWAS. So if you increase the sample size, you find more variance, and therefore the PRS will get better. So you can see it will make quite a big difference. These are expressed in terms of area under the curve. There is a limit, and the limit is defined by the total heritability of the disease that you can capture. But we're still, for most cancers, quite a long way off what can be achieved. So if we come back in 2 or 3 years' time, and there are studies, for example, in breast cancer, which are indeed aiming to double the sample size, so there will be a better PRS in 2 or 3 years' time. And of course, risk is much more than the PRS. Even for genetics, it's more than the PRS. The PRS comprises common variants that we identify using these arrays. But we know that there are also lots of rarer gene variants which are associated with risk. Of course, the BRCA1 and 2 genes that were found many years ago, but also variants in other genes. And so you really want to consider those together. They're kind of more or less independent, so you can combine them together. And of course, there may be many more here, because these you need to find by sequencing, and the sequencing has been done on a much smaller scale than the GWAS yet, so there may be a lot more there. And there are other risk factors. There are lifestyle risk factors and other things. I mean, for breast cancer, the most important other risk factor is imaging. We know that women with more dense breasts have a much higher risk than women with low dense breasts. And this has an effect which is quite similar to the PRS. So there's something like a 4-fold difference between the low risk and the high risk category. So you really want to take that into account as well. And that comes down to the question of a risk model. So our favorite risk model for breast and ovarian cancer is the Boadicea model, which does indeed combine the effects of these genetic risk factors, the mammographic density, lifestyle risk factors, family history, and to construct a comprehensive risk score. And so what it's doing is sort of illustrated here. So on the bottom, the x-axis here is the lifetime risk of breast cancer. And the red line here, this would be the average woman, or a woman aged 20 now. So they have a risk of breast cancer of about sort of 12%. So they will be at normal risk. If you consider the effect of lifestyle risk factors, that you get this green distribution. So a proportion of women would have a risk of more than 17%. That's what counts as moderate risk according to NICE guidelines. If you also include the mammographic density, the distribution gets wider. And so you can see here it's a wider distribution. Here's the PRS, which is this yellow distribution. But the widest distribution you get is if you put everything together. And now you can see that, well, two things. Well, you can see that there are quite a lot of women. In fact, more than half the women's risk reduces, sometimes quite substantially. A lot of women now are in the moderate risk category, and some have a risk of more than 30%. So they are now in the high risk category. So that really emphasizes the importance of trying to combine all these factors together. So imaging also has a long way to go, like the PRS. So there's probably a lot more information that could be captured from imaging, because density is just one measure. There are lots of other things you can measure, like calcification and masses, and sort of patterns of density. And there's quite a lot of work going on using various AI techniques to try and extract this information. And there's quite good evidence that these type of features are also predictive of risk. This is just some results from Perhall and Mikael Eriksson from the Karolinska, looking at, so here's breast density, that's a risk factor, but also things like these masses and calcifications have really quite big effects on risk. So these aren't incorporated, this is still work in progress, these aren't in the risk models yet, but they're obviously going to make a big difference to the risk models going forward. Finally, just a word about diversity. It's a very important theme in the conference, of course. The PRS distributions vary quite a lot by ethnicity. So everything I presented in the PRS development was based on women of European ancestry, where there's the most data. But again, if we look in UK Biobank, you can see, so these are the women in European ancestry. You can also look at African, East Asian, and South Asian, and mixed. And what you can see is that there's quite a big shift. So women of African ancestry have a much higher on average PRS. In fact, the mean in controls amongst African women is actually higher than the mean in cases of European women. That's also true for East Asians and to a lesser extent South Asians. They're somewhere in between, and also women of mixed ancestry. You can see that the PRS works in all these, in the sense that there's this shift in each ancestry. So there's some predictive value, but there's this shift. And this is a bit curious because, of course, women of non-European ancestry aren't at higher risk. They're, if anything, at lower risk. So the reasons, maybe it's just chance, but anyway, it's quite curious, really, that the PRS tends to be higher in non-European populations by an amount that's important, because, so you can see here that if you just applied the PRS naively to non-Europeans, you would get the wrong answer, because you'd be allocating far too big a proportion as being at increased risk than is really the case. So you need calibration. The effect size is also a bit different. So here's the data we saw before for Europeans, with this odds ratio of about 1.6. It's a bit less in Asians, but East Asians, not much less, but clearly a lot less in Africans. And there are many reasons for that. The patterns of linkage to equilibrium are different. The type of disease is also a bit different. But this sort of emphasizes the fact that we really need better, we need to improve to try and get some sort of equity, the predictive value of the PRS in these non-European populations, and there are efforts ongoing to do that. So I'll stop there. So just a few key points. So PRS provide useful and well-calibrated risk prediction. Generally, rather, at least the estimates are very accurate, but they're better in combination with other risk factors. Much less evidence for prediction of clinical outcome, and not really any, unfortunately to date at least, prediction of treatment response. It's clear that it can be a cost-effective approach for stratified screening and prevention, but there are many practical obstacles that remain before this becomes a reality. And better PRS, especially for non-European populations, is required. So I'll finish there, and I'm happy to take questions.